Hi, I'm Ben-Yaakov. This presentation is entitled Ripple Control of PWM Converter. There is a related video to this presentation, the inner works of peak current mode control, and here is the link to it, and I'm also going to print the link at the description section of the video that you are now watching. I highly recommend to watch this video because it has the basics of peak current mode and slope compensation that I'm going to use in this presentation. So what are we talking about? There are a number of control methods that are now being used in current design. The most popular one is the continuous control, I'll call it, in which we have a feedback of the average voltage compared to a reference, and there is a phase compensator. We might have also a current feedback, like in a peak current mode or average current mode. So this is the most common way of designing a controller for PWM converters. On the other hand, there is another family, a large family in fact, in which the feedback is not from the average voltage, but rather looking at the ripple or at the peak values. For example, here I'm looking at a generic case of such a control. We have the voltage at the output with the ripple on it, and then we compare it to a reference, but here this is a comparator, this is not an amplifier. So it kicks when the peak value of the voltage is equal to the reference, not the DC value. We might also have a current feedback, but this is just an addition, okay? So the idea is to look at the ripple. Now we can look at the peak, we can look at the valley, we look at the hysteresis, adaptive hysteresis. There are many ways to do it. In fact, I have here a short list of various control rely on ripple. Could be peak, could be valley, could be constant on time. This has merits to it, although here the frequency is not constant. Could be hysteresis control, looking from peak to peak. Adaptive hysteresis control, very clever control system, by the way. V square control, V square I control. There are many approaches. Now, in this presentation, I'm going to discuss the generic idea behind all these control methods. And this is an educational presentation. This is not a design guideline. There are many practical details which are missing here. I'm just giving the basic idea of the control mechanism. And the objective is to explain the basic concept of this ripple control. So here is a generic representation of the idea. We have here a buck converter, two transistors, a synchronous buck, this is the driver. We have an inductor, capacitor, and the load. Here I'm showing the ESR of the capacitor. In this case, in the basic variation of this type of control, the resistance here is very important. It is not just a parasitic element, but it's really important because the ripple that we see here, the triangular waveform, is in fact due to this resistance, okay? So it is inherent in this design of the control that you need this resistance. We'll see later on that you can get by without it, but the basic idea actually relies on this resistance. So we have this ripple, and this ripple now is compared by a comparator to some reference level. The flip-flop turns on the transistors, or the upper transistor I should say, when the clock is on. We have a clock here which is running like in a peak current mode, the continuous clock, the switching frequency, short pulses that turn on the flip-flop, which turn on the upper transistor in this case. And then when the ripple is reaching the reference level, then the comparator kicks, there is a reset, and this will be the end of the pulse. So we can see it here. These are the clock pulses. With the clock we have the ripple actually being generated because the current of the inductor is now increasing until we reach with the ripple the reference level, and then the midpoint here will go down. This is the midpoint here, will go down. So this will determine actually the duty cycle. So here is a basic LTspice schematics that shows this concept. This is a generic set reset flip-flop. The output is 1 volt here. This just this basic module. I have a reference of 1 volt. The output has a divider 4 to 1, so basically the idea is to get here 5 volts. This will be 1 volt here, which goes back to the feedback. So this is now the comparator. We have 1 volt on one side, and then we have the feedback coming from this divider on the other side of the comparator, which will reset the flip-flop, while this flip-flop is set by the pulse generator here, which is running at high frequency. It's a period of switching cycle of 3 microseconds. It's about 300 kilohertz. These are the pulses which are turned on the flip-flop, and then when the ripple here is reaching the value of after division of 1 volt, there will be a reset. Okay, now the voltage of the midpoint here is a reflection of the output here, and I'm multiplying it so that I can get various levels. Typically it'll be like 8 or 20 volt, just to look at different duty cycle. I'll talk about it later on. Now I've also added here a current source to emulate a step in the load of 1 amp. It's running actually at 1 amp because 5 volt and 5 ohms, so it's 1 amp load, and then I'm adding here another 1 amp during this transition. And here is the basic operation. What we see here is the output voltage. It's the ripple, very typical. You see that the peaks are about 5 volts, and this is because after division we have this sense voltage, which is compared to 1 volt. Well, it's not exactly at the peak, and the reason is that the comparator has some offset and delays, so it's well, it's in the couple of millivolt difference. And then when this is crossed here, this will be the end of the pulse. The turn on will be with the clock, which I'm not showing here, and the turn off is when this voltage is reaching the reference level. So this is the basic idea. Here, the input is 20 volt. This is the midpoint. The output is 5 volts, so we are talking about a duty cycle of 0.25. This is generated by the time it takes again to this ramp from here to go up to here and to stabilize the output to about 5 volt at the peak. And here is the response to a load step, 1 amp. This is the load, and you see that we have a constant output, and then we have the load changing. There is a drop in the voltage, and you see that just about within 1 cycle of the switching frequency, there is a recovery. And the reason is that once it drops, then it'll stay on. I mean, the upper transistor will stay on until we'll reach again the peak value of 1 volt at the sense point. So the response is really very nice, and this is one of the advantages of this approach, which is, I should say, I didn't say it before, this concept in a variation of it is used in many commercial PWM controller. Another question is, how fast is it, the response? And to test this, I'm adding here to the reference an excitation. This is the excitation, 10 millivolt peak, and this is a sinusoidal waveform or semi-sinusoidal waveform which is changing with time. The frequency is changing with time, like a chirp signal. I'll show it in a minute. So this is the excitation, and I'll be looking at the output to see how is the system responding to this actually AC input. And here it is. This is the excitation. This is part of it. You see the frequency is going up, and here is the output. Very nice. Constant amplitude, doesn't change that much in this frequency range. We'll see it later on. So it really works very nice. Here is a zoomed part. We see here the excitation, 10 millivolt, plus minus 10 millivolt. And we see here the output. This is of course the ripple, the 300 kilohertz. And I'm also showing here, sort of pushing it to the high frequency at 87 kilohertz. Obviously, we don't have too many points, sampling points here, so this couldn't be a very nice waveform. It's a fairly large signal, 10 millivolt, and this is for 87 kilohertz. Still, it's working okay. Well, not very elegant, but it's okay. And here, I've reduced the excitation to 1 millivolt just to show that if the signal is small, you still get a very nice response. We see here the excitation. So we really could say that the time domain response of this class of control is very good. However, surprise, surprise, if the duty cycle is 0.625, larger than 0.5, and this is because I've reduced the voltage of the midpoint to be a maximum of 8 volt, so the output is 5, the input is 8, so we have a 0.625 duty cycle, and we see here subharmonic oscillation, very similar to peak current mode. There is no direct feedback of the current, but it is, I'll show it in a minute, reflected by the ripple. So we have the same problem here, although it's not peak current mode, we do have the problem of subharmonic oscillation at high duty cycle range. So here is the explanation of what is really going on. The basic configuration is again shown here. I'm taking the output from here, voltage plus the ripple. It looks like a voltage mode control, like looking at the voltage, but if you probe into it, you realize that indeed you are actually looking also at the current. And here is the reason. You see, I can break this voltage, total voltage, into two parts, one across the resistor and one across the capacitor. Now the voltage across the resistor is a reflection of the inductor current, because the inductor current is actually passing through this resistor, okay? Assuming that the impedance here is much lower than, of course, the impedance here. So the voltage here is in effect a measure of the current, a reflection of the current of the inductor, exactly like in peak current mode. And then we add to it this voltage across this capacitor. So the total is what we have here coming to the comparator. So if you look at it, well, it looks like peak current mode, because you have an inner loop of the current, and then you have an outer loop of the voltage, exactly in peak current mode. So it's not a surprise now that, like in the peak current mode, you are going to have the problem of subharmonic oscillation. And again, this is explained in the video that I've referenced and will be printed in the description section of this video that you are now watching. So to look at it and to see that indeed slope compensation is helping, I'm generating here a slope. I could have taken it from here, because here we have a square wave, and then with a resistor and capacitor I could have generated a slope, but I prefer to do it this way. So I'm adding the slope to this sense voltage. This is the sense voltage. I'm adding the slope to it, okay? Everything else is the same, and lo and behold, the duty cycle 0.625, and everything is stable. Now, what we see now is that the original ripple is this one, and now I'm adding this slope compensation. Well, I may have exaggerated with the amount of slope that I've added, and this is just to emphasize the fact that when the ripple is higher, and since I'm looking at the peak value, then the average now of the output is away from the 5 volt. Well, it's not that much, but still it is sort of moving away, and the average is not 5 volt as I would have liked to have, okay? So this is a problem that we have here when we have the slope compensation, and in fact it is a problem with the method itself, because it's looking at the peak and not at the average. But this can be corrected, and the way to correct it is to add indeed another path of the DC component. Here I have a GM amplifier, a turn conductance amplifier. I'm comparing the output to the reference, and then I have here a capacitor. So this is like a type 1 compensator, a dominant pole compensator, which is just looking at the DC, because this capacitor is sort of averaging out all the ripple. And so this now will help to move back the value of the DC to the reference value, which is this reference value. Okay? So this is added to correct the error of the DC. And this is how I've implemented it in LTspice. Here is the GM amplifier, it's a behavioral source, current source. This is the gain, and this is the difference between 1 and the voltage sensed here. Well, I did it a little bit different. I've added here 1 volt. So at steady state, the voltage here will be 0 across this source, and the reference is 1 volt. And then if there is an error, then it will start growing or going one way or another, and then eventually it will stabilize to 0 here with this equal, with the voltage of the sense equal to 1, and then of course we are going to get the 5 volt at the output. And here is how it operates. I'm showing here the output voltage. There is again the 1 amp step load. You see that there is a drop, of course, due to the load, and there is a recovery, but as you can see, the average voltage of the output now is 5 volt, and once it's recovered, it's going back to 5 volt. Very, very neat. Now, this signal here is actually this moving reference. It is 1 plus this integrator output. So in steady state, this is 0 and the reference is 1, which is about what we can see here. There's some disturbance here, you can barely see it, when of course there is a load at the output. And now, what about the resistance that we need here? As I've said at the beginning, the whole idea is that you need ripple. To get the ripple in the conventional way, you need a resistance here. And if the resistance of the capacitor is too small, you might add a resistor. This is not a good idea. You don't want that much a high ripple at the output. You like it to be as smooth as possible, okay? So there is a way to overcome it by an additional circuitry, which is this network here, which I'm showing here, okay? It's also shown here. This is this network. And here is the idea. The voltage across this inductor looks like this. We have on one side V in minus V out, and on the other polarity we have V out. Okay, average is 0, of course. And, well, it doesn't show a 0 average, but it should be, of course, 0. And this is the voltage imposed on this network. So now I have this voltage on this R1, C1, which is causing here to have a ripple, triangular ripple due to the, of course, you have to choose correctly the R and C values to have this ripple here. Now the whole thing is now riding on the output, so you have a DC here, you don't want to inject it to this point, so this is like a coupling capacitor to get rid of the DC, so you just inject the ripple part to here, okay? By this, you can have here a very low ripple, or almost no ripple, while you actually inject the ripple here. There is another way to look at it, which is, I think, is very important to understand, and that is that this arrangement is really emulating the current of the inductor. You might say that this R1C1 is a emulator of the inductor current, because we have this voltage across this network here, and the voltage across the capacitor is in fact emulating the current through the inductor. And as you might know, this is actually the idea used to measure the inductor current without an additional sensor that is just relying on the inductor and the internal resistance. Okay, this is a well-known technique. Here, we are using it to generate just the ripple. We're interested in the ripple. The voltage across this is, of course, the average voltage across the resistor, so the voltage across this capacitor, it can be used as a measure of the inductor current. But here we are more interested in the ripple which is injected here. And in this you can implement it, and here I'm showing it with this R and C, and this is the decoupling capacitor, just to get the ripple out of here. Everything else is the same. And here it is. Just to compare the two ripples, I have shifted the ripple of the sense point, which is at 1 volt. I have shifted it by 4, so it'll be at about the same level here. And we see here, this is the ripple injected actually, okay? This is the injected ripple, while the green one is ripple on the 100 microfarad capacitor, small ripple, it's only 1 millivolt. Not only that, it is more like a ripple of a capacitor. It's not reflecting actually the resistance anymore, and therefore there is a phase shift. So in fact you cannot use it for this operation because it's not in phase with the switching cycle. So therefore, if the ripple is small, then you have to use an injection of ripple to make this circuit work. And here is the performance as a response to the 1 amp load step. Again, very nice. You see the drop in the output, it's about 25 maybe millivolts, and then in the recovery. And so again, the time domain response is very nice. And here we have a nice DC control, it's a 5 volt. And also we have a capacitor with a low resistance, low ESR. There is very little ripple at the output. You see here the ripple at the output. So this is a very nice concept for design. And indeed, they are the commercial controller which are designed according to these ideas. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.